As we keep thinking about current and voltage, I just wanted to make sure to include this figure from your textbook, which I think is very useful for helping to think about this in terms of water instead of electrons, but we have similar sorts of ideas that we think about. So if we're looking at a hose, for example, the electric current would be like the flow of water through the hose. If you could measure, how many milliliters or how many liters of water or gallons or whatever want to use come out of the end of a hose per second, that would be like measuring the current of an electrical system, right? So how much water do we get out per second here? Whereas the potential difference, the voltage that we measure, is thinking about how much pressure do we have pushing on that water. So we can see that current and voltage are going to be related to each other, but they're not exactly the same. So if we imagine that there's like a giant tank of water and our hose is connected to it, the higher that tank is, the more pressure is going to be pushing on this water. We get a higher current at the bottom, but it's really this pressure that we're measuring when we measure voltage, not necessarily the current. Whereas if there's a low pressure, because we can have a high pressure but still have a low current if our hose isn't very big, for example, or if there's a kink in it. You can still have the same amount of pressure on the hose, but your amount of current that comes out is less. Whereas if this tank is lower, there's less force pushing down on the water, and if everything else is the same, we will get less water out at the end, and the current will be smaller. So we can see that there is this relationship. So let's write this mathematically. So electrical work, in an analogy to physical work where we're moving objects around, that's a force times a distance. In electrical work, we take the voltage, which in this class at least, different places write it different ways. But we're going to use the symbol capital E to represent electrical potential energy or voltage, right? So this is our voltage. So how much force is pushing on our electrons, and times Q, which is the charge. So this tells us the amount of electrical work that's done. So in terms of units, that means a work is always given in units of joules, which is going to be equal to a volt times a coulomb, because that's voltage times charge. Another way of thinking about this is now we have a different way of writing volts. Volts is equal to joules per coulomb. All right, and so the amount of work that can be done depends on the voltage, depends on how much force is pushing on it. In a similar way, free energy, delta G, tells us about how much work can be done by a chemical system, and that allows us to make a relationship between Gibbs free energy and voltage. And I mentioned in the last video there was a relationship. Here we're going to see what the exact relationship is. So delta G is equal to the negative of the amount of work that can be done by the system, which is equal to negative E times Q, based on our relationship above. If we write this in terms of molar quantities instead, we have that delta G equals negative N, N here being the charge per molecule, right? So if you have a +2 charge versus a +3 charge versus a +1 or -1 or whatever, times capital N. Capital N here is the number of molecules. So this will be something sort of in molar quantities, times the Faraday constant, so charge per mole, times Q. So we've taken this voltage and broken it down into charge, and broken it down into how many molecules do we have, how much charge is part of this. Oh, sorry, there's no Q there. Times E, that makes more sense. So the voltage times the total amount of charge, which is based on how much charge do you have per molecule, how many molecules do you have, and then times the Faraday constant. Right, so this is if we switch this to moles, right? If we're talking about molar quantities.